First and foremost, welcome everyone to MetaGate. And we would like to apologize because of the technical issue. Okay, the class was interrupted because of some time. So we are resuming back. So first and today, the class is going to be, our main focus is going to be on the minerals ores and the methods of beneficiation. Minerals ores and methods of beneficiation. We'll be discussing on this topic. So, talking about this particular subject, this is one of the very, very important subject, okay, as far as the extractive metallurgy is concerned. And not only about extractive metallurgy, I can say that this is the fundamental subject of metallurgy as a whole. Why? Because you see, if we are not being able to extract the metals in the most efficient manner, then other processes will not start. Say, for example, if I talk about heat treatment, so what we do in heat treatment is we treat a metal, in various temperatures, and we try to basically change their mechanical properties or things like that, strengthen the metal through different heat treatment processes or things like that. But imagine that if we are unable to produce the metal itself, then what will you do with those processes? So mineral beneficiation technique is the heart of metallurgy. So this has a very, very important role to play. First and foremost in this chapter is basically divided into two parts. Okay. So the first part is going to be, we will basically talk about in the first part, we will focus on minerals and ores. We'll focus on minerals and ores, where we'll be talking about certain things like how metals occur in nature, how metals occur in nature first. Second, we'll be talking about their mineral forms. Okay, their mineral forms. And we will also be talking about the abundance and distribution. Abundance and distribution. Their abundance and distribution. So this is going to be our first focus, okay, or our first area of interest in this chapter. And second, we will be talking about the beneficiation. And in the beneficiation technique, we will be basically talking about the physical method of upgrading the ore. Like, see, I'll tell you why this is important. Physical method of upgrading the ore. Now, if I am talking about this physical method of upgrading the ore, what it means is that you see, ores are naturally occurring substances. So, in the ores only, the metals are hidden, I can say like that. So, we need to extract the metals from their ores. But not all the ores are of good quality, obviously. And that is the limitation of the nature. We cannot do anything with that. But we can do with the technology how to upgrade the ore, how to make whatever is there, how to make 100% what to say, how to use it to its optimum level. Okay, that is what we will see in our beneficiation technique, and making the ore suitable for extraction. Making the ore suitable for extraction. Right? So we'll see this. Okay. So first and foremost, let us see if I talk about that mode of occurrence. I can say about how the metals are basically how metals occur in the nature. So mode of occurrence of metals, if I talk about mode of occurrence, so this mode of occurrence of metals, it depends upon the reactivity of the metals. It depends upon the reactivity of the metals. Like, say for example, if I ask you that which metal is going to be which metal we will find free. I mean, free means in the sense that in the native form. So which metal we will find in the native form? Will that be a more reactive metal or will that be a less reactive metal? Obviously, the answer is going to be that less reactive metal are will be found in their native form, because you see highly reactive metals like sodium or potassium, they will not be found in the native form because there are many things. Okay, there are many things in the Earth's atmosphere. Say for example, there are halogens like chlorides, fluorides, all these things. There are sulfurs also. So if the metal is reactive, then it is going to react with those elements. Okay, with the other elements. Obviously, it will react with other elements and we will not find them in their native form. That is the idea. So we can say that highly reactive metals, like if I talk about sodium or if I talk about potassium, these are highly reactive metals. They are never found free. They are never found free. Found free means what? They are never found free in the native form. Okay. But on the other hand, less reactive metals, the metals that are basically less reactive metals, okay, less reactive metals, like if I take the example of gold, if I take the example of platinum, okay, they are found in the native form. Right? So one thing we basically understand from this example, that reactivity of the metals, they play a very, very important role in determining that in which form we are going to get that metal in the nature. I can say this. Okay. Now you see elements, we can divide the elements broadly, we can classify the elements into two forms. One is, I can say that one is the metals, other is the non-metals, right? Other are non-metals. So we will talk about the metallic properties also. There are certain physical properties of the metals, okay, which we will be talking about. But broadly, I can say that the metallic behavior is being controlled by certain things. Let us see what are those things. So, so elements we can broadly divide into metals and non-metals. Okay. And yes, the metallic behavior is controlled by metallic behavior is controlled by what are the things? These are controlled by, these are very important. So please note it down. These are controlled by atomic size. Okay. Second, we can say they are controlled by polarizability. Polarizability. We'll discuss each and every points in detail. So you will understand what they are. Charge on ions. Charge on ions. And fourth point is going to be the electronic structure. Right? So metallic behavior is controlled by the atomic size, polarizability, charge on ions, and electronic structure. Yeah. So see, how do we identify a metal? If someone asks us that define a metal or what what is how to describe a metal? Okay, how do you identify a metal? Okay, then see from the, so there are various ways to define metals. There is not only one way. Okay, there are various ways to define metals. Someone can say that metals have got good luster. Luster means shining property. So they shine when they are exposed to light. That is called the luster. They have good electrical conductivity. They are ductile. Obviously, metals are ductile, malleable. They have got good strength. Okay, these all are some of the, these are all what the physical properties of the metals that we are actually talking about. ठीक है, ये सब तो ठीक है, but scientifically, you know, there is a particular definition of metal from the physics point of view, which is there, that elements, we can say that metals are those elements, okay, whose electrical resistivity whose electrical resistivity increases, okay, with temperature. That means, suppose at less temperature or at room temperature, a metal is extremely conducting. So it is conducting electricity. But when I eventually increase the temperature, its electrical conductivity is going to decrease, or I can say that conversely, I can say that its electrical resistivity is going to increase. Now, there is basically reason behind it. Say, for example, if this is a so we will not talk much of physics here, but okay, let us see why it happens. So you see, if this is a metal and this is the cross section I am talking about. Now, if I give this metal temperature, so giving temperature is, or rising the temperature of a particular substance is nothing but giving energy to it, right? I am providing thermal energy. So as we are providing thermal energy, there is going to be more vibrations to the atoms also. Whatever atoms are present inside, they are going to vibrate with respect to their mean position. So more vibration means actually, the more they are going to vibrate, obviously the electrons inside will also vibrate more. Okay, because they are also getting that energy. So the electrons will vibrate, and the electrons, suppose the electrons, they were, before I provide them the temperature, suppose the electrons were flowing in a straight line. Okay, undeviated and in straight line. All the electrons are flowing like this. Okay, in the straight line. But when temperature is provided to them, what is going to happen? They will vibrate about their mean position, and there is going to be zigzag motion, more zigzag motion or random motion in them. So there is going to be also collisions between them. Okay, so this is going to actually, what it will do is that it will reduce the rate of flow of electrons. And if the rate of flow of electron is reduced, that means obviously the electric flow or the current flow is going to get reduced. So I can say that electrical resistivity increases. Okay, so this is basically the reason behind why this happens. But you see, from metallurgy point of view, it is not that important. So we will not focus much on this. Uh, but obviously, we should discuss the why it is happening. So that is why we have discussed. So so some of the common practical properties of metals, you can note it down, that common practical properties of metals, and we can note it down here. Say, for example, if I'm talking about, one property is going to be our metallic luster. Metallic luster. Okay. Another property is going to be our good electrical conductivity. Good electrical conductivity. So when I'm talking about good electrical conductivity, We are basically talking about the conductivity of the metal in the room temperature. Okay. Good mechanical properties. Metals will also have good mechanical properties. And in the good mechanical properties, we will have ductility. Okay. That is percentage elongation. And you have malleability. Okay. Ductility, malleability. Apart from that, you will have good strength. Okay. So there is good strength. There is good hardness. Metals are also hard. Okay. Impact strength is also there. Good impact strength. So these are all the various properties of metals that we can talk about. Okay. Okay. Now, suppose we are discussing about them. Okay. But there are certain exceptions also. There are certain exceptions also. What are these exceptions? Okay. We need to understand. Like there are some of the metals which are brittle. Like I said, that metals are ductile. Okay. But mostly metals are ductile, but some of the metals are brittle also. What are those metals? Like if I'm talking about arsenic and if I'm talking about bismuth, these are basically brittle metals. Okay. Okay. This is among the metals I'm talking about. Now there are certain non-metals which shows metallic properties. Non-metals. So these points are very important. Non-metals showing metallic properties. So these points are very important. We need to understand them. Like if I'm talking about iodine. Now iodine is a non-metal, but it has metallic luster. So you see, if I say that metals should have metals are those materials or those materials which have metallic luster. So that means going by that definition, iodine will also become come under metal, which is not true. So iodine is having metallic luster. So why those definitions have got certain demerits that I actually try to focus in. If I talk about graphite, so graphite is a non-metal. Okay, but it is having good electrical conductivity. This is having good electrical conductivity, graphite. Okay, because there are some of the electrons which are not that strongly bonded. So those electrons actually, in case of graphite is basically a layered structure. Okay, so the structure is layered and the electrons can flow easily. And diamond. If I'm talking about diamond, you see, so diamond is a non-metal which is actually extremely hard. So this is not a metal. This is a non-metal only. But you see, diamond is one of the hardest material. So which we use. That is why diamond is used extensively. Okay, in cutting objects like diamond cutter. Okay, so okay, these things are there. Now, we need to see the trend of metallic nature in the periodic table. We will see the trend of metallic nature in the periodic table. Trend of metallic nature in the periodic table. Now, metallic character increases. Always remember, metallic character is going to increase down a group in the periodic table. So I can say why it increases, we will talk about it. Metallic character increases number one down a group in the periodic table. What I mean by this? What I mean by this? See, if you see the periodic table, so in the group 1, you have, in the first group, you have uh, hydrogen followed by lithium, sodium, potassium, okay, then rubidium, uh, cesium, and francium. Okay, so forget about hydrogen. Apart from hydrogen, you see lithium, sodium, potassium, rubidium, cesium, francium. These are all, we can say, they are nothing but metals. Okay. Now, what I have written here, metallic character increases, and metallic character increases down a group. That means as I am going from lithium to francium, okay, as I am going from lithium to francium, what is happening? I can say that the metallic character is increasing. So, like lithium, the metallic character is less compared to sodium, and sodium's metallic character is less compared to potassium. Potassium's metallic character is going to be less compared to rubidium. Rubidium's metallic character is going to be less compared to cesium, and cesium is going to be less compared to francium. So if I'm talking about the metallic character down the group, the element which is going to be lowest in the group, that will have the highest metallic character, and the element which is going to be at the top in the group, that will have the lowest metallic character. So this is the trend that is basically followed in the periodic table. And if I'm talking about in the period, then what happens? See, in the period, the general trend is, okay, from right to left in the period, the metallic character increases. From right to left in the period, the metallic character increases. What it means, we will take an example and understand. Okay, we'll take an example and understand. Say, for example, I am talking about one period which is sodium, magnesium, okay, sodium, magnesium, aluminium, silicon, phosphorus, then we have sulfur, chlorine, and argon. So if I'm talking about these elements, this is a particular period. Now, if I move from right to left, then I can say that what happens? Sodium is more metallic. Sodium is more metallic compared to magnesium, which is more metallic compared to aluminium, which is even more metallic compared to silicon. Silicon is more metallic compared to phosphorus. Phosphorus is more metallic compared to sulfur. But you see, ultimately, up to silicon, these are non-metals. So the point is phosphorus, sulfur, chlorine, argon, they are becoming non-metal. Okay. So what happens is, if I am talking about the period, then you see only sodium, potassium, and aluminium. They are the metals. After that, they are non-metals. Okay. So what is happening is, I can say that as in the period, as we are moving from left to right, we are basically moving from the metals to non-metals. So that is the trend. So that is why we have written from right to left in the period, the metallic character increases. Or conversely, I can say that. Conversely, I can say that from left to right, the metallic character decreases. Okay. Now, these are the things that we have seen that, okay, down the group, the metallic character increases. And if I am moving from right to left in the period, the metallic character decreases. metallic character increases from right to left in the period, the metallic character increases. But now we should ask the question why? Why this is following this kind of a trend? Okay. Okay. Now let us focus on this why part, because understanding this why part is very, very important. Why it happens? Because you see down the group, what is happening down the group? If I just take this example, like lithium, sodium, potassium, rubidium, cesium, francium. So if you move down the group, then your atomic size is increasing. Say for example, lithium atom, this is the atomic size. So sodium atom is more compared to lithium. Potassium atom is more larger compared to sodium atom, and like that. So we are increasing the atomic size as we are moving down the group, the atomic size is increasing. So you can say that down the group, what is happening down the group? A, the atomic size increases. The atomic size increases. And as a result of increasing the atomic size, the ionization energy decreases. What is meant by that? What is meant by that? Okay, now let us understand. Suppose this is a lithium atom, okay? And ionization energy means, suppose I have taken just one lithium atom. Now I would like to convert this lithium atom into lithium plus, Li plus. That is the lithium ion. So initially I have taken lithium atom. Now I want to convert this lithium atom into lithium ion. Okay. That means I want to take one electron out from its outermost shell in the lithium, from the lithium atom. So suppose this is the electron. I want to take this electron out. Okay, this is the electron. I want to take this electron out. Now, ionization energy means the amount of energy that I need to give in order to take this electron out from its outermost shell. That is called the ionization energy. So you see, if the atomic size is small, then what happens? You see, atomic size small means nothing but nucleus is there in the middle of the atom. There is going to be nucleus. And in the nucleus, there are protons. So protons are positively charged. So that is why I can say that the nucleus as a whole, it is positively charged. We know that. So this nucleus is going to attract the electron, obviously, electron of the outermost shell. The nucleus is going to attract the electron. Now, when this nucleus is attracting the electrons of the outermost shell, then what is happening? There is going to be strong electrostatic force of attraction. Now, if the atom is smaller in size, what it means is that the shell is basically the outermost electron is closer to that of the nucleus. Now, if the outermost electron is closer to that of the nucleus, that means the force of attraction is more. The force of attraction is more, or we can say conversely, that the electron is bound more in a more strong manner. Okay. So electron is bound or held in a more strong manner. So in order to take this electron out, I need to give a lot of energy. We need to put in a lot of energy in order to take this electron out from its outermost shell. This is number one. But if this atom is, say for example, if instead of lithium, if I have taken, suppose rubidium. So rubidium is a larger atom. It is having a larger atom. So the electrons in the outermost shell, what is going to happen to this electron? This electron is not bound that strong. Okay, so comparatively less energy, if I can provide, I can actually take this electron out from its outermost shell more easily. Very easily I can take. So I can say that the ionization energy of lithium is much more compared to the ionization energy of rubidium. That means, what it means is that rubidium will give one electron very easily, or rubidium is going to get converted to rubidium ion more easily compared to lithium. Okay. So that means rubidium is more metallic in nature compared to lithium. Got the point? So now let us understand. So metals, reactivity of metals is basically, I can say reactivity of metals, they are basically dictated by that how easily metals lose electrons, how easily metals lose electrons, right? So the more easily a metal is going to lose electrons and get converted into a metal ion, okay, we can say that, or we will say that it is more reactive. That metal is more reactive, right? So now reactivities of metals. Uh, Now talking about the reactivities of metals, as far as metallurgy is concerned, we will talk about three main criteria. Okay. The first criteria that we are going to talk about is what we call the reversible electrode potential. Reversible, electrode, reversible electrode potential. This we will talk about. Second, we will be talking about free energy of formation. Free energy of formation. Free energy of formation of oxides and sulfides. Free energy of formation of oxides and sulfides. And third, we will be talking about the electronegativity. We'll be talking about the electronegativity. So first, we'll be talking about the reversible electrode potential. Second, we'll be talking about free energy of formation of oxides and sulfides. And third, we'll be talking about the electronegativity. So what is meant by reversible electrode potential? Let us see. If I first talk about this only, reversible electrode potential, what is it? What is this reversible electrode potential? Okay. So reversible electrode potential means the tendency of transition of a metal into its metal ion. That means what happens, you see, if there is a metal, okay, like I said that this metal will always have a tendency to get converted into metal ion. Okay, metal ion plus it is going to release electrons in its aqueous solution or salt solution, right? Now, I can say that this is metal solid getting converted to Mn plus Ne minus, right? Say for example, if I have taken sodium, so this sodium in its aqueous form is going to get converted to Na plus and it is going to give one electron. Okay. So this tendency of this sodium to solid sodium or the sodium atom to get converted into the Na plus ions, sodium ions, is what is making this sodium metal, I can say. So higher tendency to form higher this tendency of a metal to get converted into its ion, I can say higher is the reactivity. So you can write higher tendency to form ions, higher is going to be the reactivity. Higher is the reactivity. right? Okay. Now, let us take this example forward in aqueous solutions. Let us talk about what happens in aqueous solutions. Say, for example, if I'm talking about a metal, so this metal is going to, like I said, it is going to get converted to Mn plus and N times of E minus, right? So more the E naught value, more negative it becomes. So the metal is going to be more reactive. That means what it means? It means that that metal is going to give up the electrons more easily. More negative the E naught value is, that means the metal is becoming more reactive. Okay. Now there is a series which we call the electrode series or electrode potential series. Okay. Or sometimes we simply call it electrode series. Okay. Now this is basically based on hydrogen scale. Based on hydrogen scale. So hydrogen we take as 0, and all the metals which are lying above the hydrogen are more reactive compared to the metals which are lying below the hydrogen. So top metals are highly reactive metals and bottom metals are noble metals. So you can just, if hydrogen is your, uh, is your base, or I can say is the point of reference, then the metals above the hydrogen, we call them reactive metals, and the metals below the hydrogen are less reactive metals. So that is the idea, main idea, right? So if I talk about the reactivity of the metals, if we discuss in general about the reactivity of the metals, then I can say that potassium is more reactive compared to sodium, and sodium is more reactive compared to magnesium. Magnesium is again more reactive compared to aluminium. Aluminium is more reactive compared to zinc. Okay, zinc is more reactive compared to iron. Iron is more reactive compared to copper. Copper is more reactive compared to Ag or silver and Au. Okay, so this is the reactivity of the metals we can talk about. This is the reactivity of the metals. So metals, like see in the reactivity series, the main thing is metals higher in the series, okay, they forms ions easily. I can say they are forming the metal ions easily. So I can say forms ions easily. Number one. And number two, strong reducing agents. So more reactive a metal is, that metal is going to be more reducing. So I can say they are strong reducing agents. Right? Because what happens, the metals, they are releasing electrons. So this is the concept. Now, if I talk about, now this is one way of identifying that the reactivity of the metals. Okay, this is one way of identifying the reactivity of the metals. But apart from that, there are some other ways also of identifying the reactivity of the metals. And now we will be talking about some of the other ways. Okay. One way of talking about the reactivity of the metal is free energy of formation of compounds. So let us see what it is. free energies of formation of compounds. This is very, very important. And I tell you, this is the basis of the origin of Ellingham diagram. So when I'm talking about the free energy of formation of compounds, here we basically talk about the stability of oxides and sulfides. Mostly we will be interested in talking about the stability of oxides and sulfides. We mostly talk about the stability of oxides and sulfides. Say, for example, let us take one example here. So if I take the example, like I'm talking about, suppose, aluminium oxide. So 4 times of Al plus 3 times of O2, we are given Al2O3, 2 times of Al2O3, right? So this is one oxide, aluminium oxide, where 4 moles of aluminium is reacting with 3 moles of dioxygen or O2, and we are given 2 moles of Al2O3, right? And if I talk about Fe plus O, that is 2 moles of iron reacting with 1 mole of O2, and we are getting basically 2 moles of FeO, right? Iron oxide. So these are oxides. Aluminium, this is aluminium oxide, this is iron oxide. Now, if I compute the del G naught value, that is the Gibbs free energy value or the energy of formation value, okay, for these oxides, and if I see that which oxide is more stable. Now, how to see that which oxide is more stable? The oxide which will have a less or more negative del G naught. The oxide which will have more negative del G naught. More negative del G naught means that the free energy is more negative. So that oxide is going to be more stable. But here, see, I will not be able to directly calculate here, because here 4 moles of aluminium is taking up 3 moles of oxygen and giving 2 moles of Al2O3. And here 2 moles of iron is basically reacting with 1 mole of oxygen. Now, what Ellingham did was that he said that this kind of, if I kind of find out the del G naught value of this equation, this balanced equation, it is going to be a bit, this is going to be wrong. Because here the aluminium is reacting with 3 moles of O2. And here the iron is reacting with 1 mole of oxygen. So first and foremost, what Ellingham pointed out is that the moles of oxygen should be same. So if I convert this, topmost reaction, if I say that 4 by 3 of aluminium is reacting with 1 mole of O2, okay, to get 2 by 3 moles of Al2O3. And this we can write as it is, like 2 moles of iron reacting with 1 mole of O2 to give 2 moles of FeO. Now, this equation I can actually, of this equation, I can find out the del G naught value of this one, del G naught 1, okay? And of this, I can find out the del G naught 2. And we can now compare that which is having a negative del G naught or which is having lower del G naught value. And then I can say that yes, this oxide is more stable compared to the other, right? So the general idea is that if we are having a metal M, okay, and if it is reacting with 1 mole of oxygen, okay, so I can write that 2x by y of M reacting with 1 mole of oxygen to get 2 by y of mxoy. MXOY. So you can take the X and Y. What are X and Y? So see, if I'm talking about Al2O3, X is equal to 2 and Y is equal to 3. So X is equal to 2 and Y is equal to 3 in Al2O3. Al2O3. So if you put the value of that, so you see directly if we put the value like 2 into 2 is 4 by 3. So 4 by 3 of aluminium plus O2. What we got? 2 by Y. So Y means 3. 2 by 3 of Al2O3. You see, just this equation only we have got in the previous when we made the oxygen as 1, right? So this is the final. You can remember this 2x by Y of M plus 1 mole of O2 giving you 2 by Y of MXOY. Okay. So this is the equation for calculating or computing the del G naught value in Ellingham diagram. Okay. This part I think we have understood. Now we'll be talking about Ellingham diagram in detail also in our subsequent classes. Why EMF? Now we need to understand one thing. Why EMF series is not enough? EMF series tells us about reactivity of metals. That is true. If I am talking about the EMF series or the electromotive series, it talks about basically the reactivity of the metals. But it tells us about the reactivity of metals in ionic solutions or in ionic medium. So you can write EMF series tells us about the reactivity of metals in ionic solutions. It tells us about the reactivity of metals in ionic solutions or ionic medium. Many compounds are not purely ionic. The problem is there are many compounds which are not purely ionic. Most real chemical bonds are basically partially ionic and partially covalent. Okay. So EMF series is not good for that. So you see the tendency of an atom. So electronegativity, we will be apart from like instead of using the EMF series, what we will basically talk about more is basically electronegativity. Electronegativity. This is better approach. Why? Because this is good for bond polarity and bond character. So electronegativity means what is electronegativity? You can say the tendency of an atom in a molecule to attract shared pair of electrons towards itself. Say for example, let us understand this. So there is CH bond, carbon and hydrogen. So out of carbon and hydrogen, which is more electronegative? We know that carbon is more electronegative compared to hydrogen. So the shared pair of electrons between carbon and hydrogen, okay, it is going to be more towards the carbon. Okay. So it is going to be more towards the carbon and less towards the hydrogen because carbon is more electronegative compared to hydrogen. Okay. So this is the concept of electronegativity. Simple. Okay. Now, there is one very important, what should I say, a very important concept, okay, which we should discuss here, and which is nothing but Pauline's. This is called Pauline's concept. Pauline's concept. So, what is Pauline's concept? What is Pauline's concept? This concept was given by Linus Pauling. This was given by Linus Pauling. And he said that when two atoms form a bond, okay, suppose there are two atoms, X and Y, forming a bond. Now, if this bond is completely covalent, is purely covalent, which is very, very rare. I mean, no bond is purely covalent. There will be some ionic character inevitably there is going to be some ionic character involved. When the two bonds are going to be purely covalent, see, you can say that the two bonds will be 100% covalent. Not 100% covalent is not possible at all. Like more, and means it's close to 100% covalent if the elements are same, like they are having the same electronegativity. Say, for example, I'm talking about Cl, chlorine bond. Yes, that is more covalent. But see, whenever there is going to be electronegativity, okay, between the two bonds, so that is going to give that molecule, I can say, a polar nature. Say, for example, if I'm talking about H2O, even water, so it is having a polar nature, right? So because this is a hydrogen atom, these are the oxygen atoms. So oxygen atoms are delta negative, delta minus, we know that, because the shared pair of electrons between the oxygen and the hydrogen atoms, okay, the electrons are more towards the oxygen atoms, because oxygen is more negative, okay, more electronegative compared to hydrogen. So this side also, the oxygen is more electronegative compared to hydrogen. So hydrogen is having a 2 del plus ion. Sorry, the charge, I can say. So delta means is very small. So, but anyway, this is covalent bond only, but there is having some ionic character in it. So it is not 100% covalent. That is the idea. So Pauling said, he said that when two atoms form a bond, if purely covalent, when two atoms form a bond, okay, if purely covalent, then what is going to happen? If purely covalent, the bond energy is expected to be of E. So the bond energy E, the bond energy is E. But if partially ionic, bond energy is higher than expected. But if there is some partial ionic character, if there is some partial ionic character, the bond energy increases. The bond energy increases. So the extra bond energy, I can say, extra bond energy, the extra bond energy, it is going to be directly proportional to the difference in electronegativity. Why? Why that is so? Because you see, extra bond energy, it is directly proportional to the difference in electronegativity. Why it is? Because if there is difference in electronegativity, because of the difference in electronegativity only, what is happening? The ionic character is coming into play. So Pauling said that earlier also, that more the ionic character, the bond energy is going to increase more. So from E, it is going to overshoot E, and some extra energy will come from the ionic nature of the bond. Okay. So if there is more electronegativity between the two elements, then there is going to be more bond energy. So I can say, conversely, we can write that the delta E is going to be proportional to XB minus XA whole square. Okay. So where this XB and XA are nothing but the electronegativities of B and A respectively, right? So relative reactivities and modes of occurrence of metals in nature. Now we will be talking about some very important ideas or topics. So the position of metal in the electrochemical series, it basically decides how reactive the metal is, whether it occurs free or in the combined form, and in what type of mineral it's found in. Okay, let us basically see one thing. Suppose I am talking about highly reactive metals. Highly reactive metals. Suppose we are talking about highly reactive metals. So when I talk about highly reactive metals, say for example, I'm talking about lithium, sodium, potassium, rubidium, cesium, calcium, strontium, okay, barium, magnesium. These are all highly reactive metals, we can say. Um, so they will have very high electrode potential, very high negative electrode potential, very high negative electrode potential, right? And they will also have very important. I want you to note these points down. One is very high electrode negative electrode potential. They will have very large negative delta G of formation. They'll have very large negative delta G of formation of oxides, you can say, and strong tendency to lose electrons. They'll also have a strong tendency to lose electrons. That means they will like to lose electrons means what? They will like to convert very easily to ions. Okay, that is the idea. Now, these highly reactive metals, like highly reactive metals, these highly reactive metals will basically, what will they do? They'll mainly be found in the nature as chlorides like NaCl, sodium chloride. Okay. They'll be found as carbonates. So highly reactive metals are found as chlorides. They are found as carbonates like calcium carbonate. Sulfates. They are also found as sulfates like magnesium sulfate. Okay. And they will also be found as aluminosilicates. Okay. Now, simple oxides are rare. In case of very highly reactive metals, simple oxides are rare. Why? Because they react with acidic oxides. Because they react with acidic oxides. Say, for example, let us take an example in order to understand. If I'm talking about CaO, calcium oxide, so calcium is very highly reactive metal. That is why we have seen that they are found in carbonates, in the form of carbonates, calcium carbonate. Now, if I'm talking about calcium oxide, suppose, yes, abundant oxygen is present in the Earth's atmosphere. So suppose, let us suppose that calcium has formed, has reacted with oxygen, and it has formed calcium oxide. Okay. Now, this calcium oxide will not be in this form, because you see, apart from the calcium oxide, there is another oxide which is also abundantly present, which is silicon oxide, SiO. So this calcium, because calcium is a very reactive metal, so this calcium oxide is going to instantly react with SiO2 and it will form calcium silicate, CaSiO3. So you see, ultimately you are not finding the oxides, simple oxides you are not finding. Okay. This is important to understand. Now, another thing which is important to understand is if I am talking about moderately reactive metals, let us understand. Moderately, moderately reactive metals. If we are talking about moderately reactive metals. Right. So moderately reactive metals means, say for example, I'm talking about iron, we are talking about zinc, we are talking about Mn, we are talking about chromium, and we are talking about aluminum, things like that. So these will be, they will be stable in their oxides form. Say for example, iron we get as Fe2O3, mostly Fe2O3. Sometimes we also get as magnetite Fe3O4. But you see, hematite is most common in case of iron, and aluminium Al2O3 will get. Okay. Apart from that, you will find when I'm talking about moderately reactive metals, they will be in their oxides form. They'll be in their sulfides form. So you will find them in their sulfides form. Say, for example, if I'm talking about zinc, it is present as ZnS. Now, I want all of you to comment below what is called ZnS. See, if I'm talking about the zinc ore, so what is zinc ore known as? Okay, that the term I actually want to hear from you. So please comment below. Is zinc ore, what zinc का ore का क्या नाम है? Right. And sometimes we will also get carbonates. Okay. Now, why oxides are common? Why oxides are common? Now, why I'm asking this question to you, like why I asked that why, what is the name of the ZNS? Because these kind of questions are very, very, you see, common as far as PSU exams like SAIL is concerned. Even in GATE also you expect, like they will give in the match the following, the names of the metals in one side and the course names in the other side, and they'll ask you to just simply match them. So PSU's exam में भी ये बहुत common है. So I want all of you to practice such questions, keep practice. And in the best way to, practice questions is through the class only. So please comment below. Now, see, where sometimes why these oxides? Like say for example, I told in the previous section when we are talking about the more reactive metals, I said that at that time the oxides are not that common. Say for example, sodium. So sodium, you will not find sodium oxide so naturally occurring. It is not very common. You will find sodium reacting with chlorine, NaCl, it will become NaCl. Or calcium, you will not find as calcium oxide. Rather than you will find calcium carbonate, or you will also find calcium silicate, because calcium oxide will react with SiO2 and it is going to form calcium silicate. Okay. Now, in this case, because they are moderately reactive, their oxides are common. Okay. So they are not like reacting with other substances because they are moderately reactive and oxygen is abundant. Like, and if I am talking about less reactive metals, if I'm talking about less reactive metals, say for example, if I talk about the copper, if I talk about mercury, and if I talk about Ag, that means silver. They are basically, you see, less reactive metals, you will find them in their sulfides form. Okay. So copper sulfide, these are very common sulfide, CuFeS2. This is called chalcopyrite. Okay. So sometimes they are also found in their native state. Native state means as it is, not combined. And there are some metals which are basically, we call them noble metals. Noble metals. Noble metals means they are very, very less reactive. Very less reactive. Gold is there, platinum is there, and silver is there. You see, why we use so much gold? One is, see, gold is so much, it has got an aesthetic value. Obviously, it has got aesthetic value. So that is why gold is extensively used in jewelry. But apart from that, apart from the aesthetic value, another thing is also there, that gold is a noble metal. So you see, that is why the gold jewelries, they can be used for so long, because it is not oxidized easily, because gold is not so reactive. Compare the gold with iron. So if someone wearing the iron jewelry, so it is going to rust like anything, right? So in 1 year, the color is going to change completely. It is going to corrode, obviously. So because iron is more reactive compared to gold, even copper is also more reactive compared to gold. So gold is, we can use so much gold as a jewelry, because see, gold is not having, even silver is also like that. They are noble metals. So they do not react with oxygen readily or so easily. Even if they react, they take a lot of time to react. So it is not that common. Okay. So this part, I think, is now they these metals you will find in their native state or in their native form, I can say. Right. Now, now we will basically talk about the definition of minerals. What is known as minerals, or what we mean by minerals. So if I talk about mineral as a whole, if I talk about mineral as a whole, I can say that minerals are naturally occurring, they are naturally occurring inorganic compounds, naturally occurring inorganic compounds, and they also have fixed chemical composition. So these 3 points you need to remember while defining minerals. That minerals are naturally occurring inorganic compounds, and they must have fixed chemical composition. And they will have definite physical and chemical properties also. We'll see each and every part. Okay, we'll see. Say, for example, if I'm talking about Fe2O3. So let us see. Yes, Fe2O3 is hematite. So hematite is naturally occurring, number one, inorganic compound. Obviously, it is inorganic compound. It has got a fixed chemical composition. You can see that Fe2O3, 2 moles of iron, basically mixing with or reacting with 3 moles of oxygen, forming this compound. It has got a fixed chemical composition. It has got physical and chemical properties. So there are definite physical and chemical properties of hematite, right? So all these criteria are fulfilled, and then I will call hematite a mineral. Similarly for CuFeS2, that is chalcopyrite. So this is having a fixed chemical composition. Obviously, this is naturally occurring. Okay, and it is an inorganic compound, and it has got definite physical and chemical properties. Okay. Similarly for Al2O3. So these are all examples of minerals. Okay. Now minerals we have defined. Now let us see what is the definition of ore. Ore is something which we have heard many times. Ore. Now what is ore? We can say that a ore is nothing but it is a mineral or an aggregate of minerals from which metals can be economically extracted. So I can say ore is nothing but they are also minerals. Minerals, but from which metals can be metals can be economically economically extracted. Now this economically word is very, very important. So metals, see, I am not saying from which metals can be extracted. Okay, there may be many minerals from which we can extract metals. But whether that metal extraction is going to give us any profit or not, that is most important to ask. That is very, very important in order to ask. whether that is going to fetch us any profit or not, right? Okay. So I can say that, so ores are also minerals, but from which metals can be economically extracted. So from this point, I can say one very important conclusion. What is it? We can say that every ore is a mineral, but every mineral is not a ore. Every ore, I can write it. Every ore is a mineral, right? But every mineral is not a ore, right? Remember this step. Okay. Now, factors affecting economic extraction. What are the factors that will determine the economic extraction? So, factors affecting the economic extraction. Factors affecting the economic extraction. So, one factor is going to be the percentage of valuable metals in the ore. So, I can say percentage of valuable metals in the ore. Percentage of valuable metals in the ore. Second is nature or form of metal, nature or form of metal in ore. Okay. Third is basically percentage of impurities. Percentage of impurities. Fourth is physical condition of the ore. What is the physical condition of the ore? Fifth is basically location and size of deposit. Very, very important. Location and size of deposit. You must know that there is a good bauxite deposit in Kashmir, but you see it is not, it is inaccessible. Inaccessible, why? Because transportations are not so much good. We cannot make so much extensive roads or road networks in the mountains. So if your metal deposit is in such a location where your transportation is not good, then extraction is not going to be much benefit. So transport facility has to be there. Okay. And market value. The metal must have good market value. Market value of metal. Right. So these are some very important points for the factors affecting the economic extraction of the metals, we can see. Okay. Now, mineral exploration method. We will see mineral exploration method. We'll see what are these mineral exploration methods. One is magnetic methods. We use magnetic methods. We use electrical methods. And we use electromagnetic methods. right? Now, apart from this, we will see each and every methods that we are discussing here. Apart from this, there are some other methods also that we will talk about briefly. And what are these methods? Like we use gravitational method, gravity method. We use seismic method, and we sometimes also use radioactive method. But these are limited. These are limited, but sometimes used. So let us first talk about the magnetic methods. Let us first talk about magnetic methods. So what are magnetic methods? So magnetic ore deposits. So you see what happens if a metal is magnetic, right? What is going to happen if a metal is magnetic? Uh, you see our earth itself is having a magnet. Our earth is having a magnetic field, its own magnetic field. Okay, earth has its own magnetic field. You know that. So, like if this is the earth, then the idea is we know all know that as if there that how is the earth's magnetic field? As if there is a bar magnet inside the earth. There is a bar magnet, and in the north pole, in the north side of the earth, it is the south pole of the bar magnet, and in the southern side of the earth, it is the north pole of the bar magnet. So the earth's magnetic field is something like this. Okay, it is something like that, and we all know that the magnetic lines, they will originate from the north pole, and or the north side, this is the dipole, I can say, uh, of the bar magnet, and they will enter into the south pole. So this is the Earth's magnetic field that we have drawn. Now, if there is a magnetic ore, which is also magnetic, say for example, I am talking about hematite. Hematite is a magnetic mineral, Fe2O3. If I am talking about ilmenite, ilmenite is a magnetic mineral. Now what will they do? They will basically interact with the magnetic field of the earth. They will interact with the magnetic field of the earth. Okay, this is exactly what is going to happen. Just a minute, we'll discuss it. Okay, now let us see. The magnetic ore deposits, I can say, the magnetic ore deposits the magnetic ore deposits, they disturb the Earth's magnetic field. Disturb the Earth's magnetic field in their vicinity. Right? They disturb the Earth's magnetic field in their vicinity. Now, which ores are magnetic? Which ores are magnetic? So we have magnetite. Sorry, actually, I said hematite. Hematite is like magnetite is more magnetic. So it is basically Fe3O4. Fe3O4, magnetite. Magnetite is more magnetic. Okay, so please rectify that part. It is magnetite. So, okay, magnetite. Which ores are more magnetic? Magnetite, nickel bearing ores, nickel bearing ores, and we have cobalt bearing ores. These are basically our magnetic ores, I can say, right? These are directly magnetic. Now, some of the ores are indirectly, we can say, we can basically get them uh, through the magnetic method only. Okay, but not directly. The ores are not magnetic. Like these are indirect method. I tell you how. Why indirectly? Say for if I am talking about the gold. Now gold is not magnetic itself. Or if I am talking about platinum, these are not magnetic. But they have in their ore, they often contain magnetite, which is Fe3O4. So gold and platinum, alluvial deposits, alluvial deposits. So they often contain, magnetite. They often contain magnetite, which is Fe3O4 grains. And see, by this magnetic technique, you can detect the magnetite. Okay. So, and in that region only you will find the gold and platinum. Okay. So, what are the instruments used? So, instruments used are important. So, please note it down. Instruments used. What are the instruments used? One is magnetometer. We use magnetometer. And another is what we use? We use variometer. Magnetometer and variometer. Now these instruments measures variations in vertical magnetic intensity as well as horizontal magnetic intensity. Let us understand what is vertical magnetic intensity, what is meant by vertical magnetic intensity and horizontal magnetic intensity. So uh, say for example, if I am talking about, so this is a magnetic curve. This is the curve. Okay. Okay. So this is this is our vertical intensity curve. Vertical intensity curve. And we will also have a horizontal intensity curve. And the horizontal intensity curve is going to be something like this. So here we are basically showing the two parts. One is the vertical intensity curve, another is the horizontal intensity curve. Right. So you see the vertical intensity curve, it is basically going to help. The vertical intensity curve, it helps detect the presence of being. Okay. So vertical intensity curve is going to, so intensity of what? These are magnetic intensities we are talking about. Okay. Magnetic intensities. So the vertical intensity curve is going to detect the presence of the ore. And the horizontal intensity curve, it talks about the depth and orientation of the ore. It talks about the depth and orientation of the ore. So vertical intensity curve and horizontal intensity curve, right? So, okay. Now let us talk about the electrical methods. Electrical methods. So if I talk about electrical methods, difference in electrical conductivity or resistivity. So electrical methods is, it basically talks about the difference in electrical conductivity or resistivity between ore body and surrounding rocks. Between ore body and surrounding rocks. So that is the basic idea. Now, what happens here? We need to understand. So there are some of the ores, some ore deposits, especially if I talk about sulfides. So some ore deposits, especially sulfides. Some ore deposits, especially sulfides, if I am talking about, they have, number one, very high electrical conductivity. So sulfides are very high electrical conductivity. Very high electrical conductivity they will have. And second, much lower resistivity than the surrounding rock. Obviously, when they are having high electrical conductivity, they will have comparatively much lower resistivity than surrounding rock. Than surrounding rock. Right. Now let us understand that how we detect it. Say for example, if I'm talking about what kind of ores, now I previously only we talked about sulfide ores. So what are the sulfide ores? The sulfide ores are like chalcopyrite, like CuFeS2. This is chalcopyrite. Galena, like PBS. Okay. And C is basically sphalerite, like zinc, ZNS, zinc sulfide. So they have much higher conductivity than rocks. So if I'm talking about CuFeS2, it is having much higher conductivity compared to the surrounding rocks. Similarly, if I'm talking about galena, which is nothing but PBS, it is having much higher conductivity compared to the surrounding rocks. Similarly, if I'm talking about ZNS or the sphalerite, it is also having much higher conductivity compared to the surrounding rocks. Now, how measurement is done? We also need to understand how we measure or how measurement is done. How measurement is basically done. Right. Now, what we do is that we either we pass the direct current or alternating current, whatever it is, DC or AC, is passed into the ground through two electrodes. So DC or AC is passed into the ground through two electrodes. Two electrodes means one is going to be positive, another is going to be negative. So you all know that current is flowing from the higher potential to the lower potential always. So electric current is going to flow, and more the potential difference is going to be there, more current is going to flow through it. Right? Like that. So potential difference is measured using a voltmeter at surface. And from current and voltage, we calculate the resistivity. Okay. We calculate the resistivity. Now that part is not, we will not focus much on this, how we can do this kind of things. Main our focus is going to be, suppose you have plot the resistivity versus the distance. So this is the distance and this is the resistivity. Okay, so in the y-axis you have put the resistivity, in the x-axis you have put the distance, right? So this is resistivity versus distance plot. Now you will find that the resistivity is constant for a substantial portion. Suppose there is a dip in the resistivity at a particular point, sudden dip, and then also the resistivity is becoming again constant throughout the ground. What this dip indicates? This dip indicates that there must be some ore present, that is sulfide ores present. Why? Because these ores are having less resistivity, and that is why this dip is actually happening. So it basically tells you that there must be some sulfide ores in the form of PbS, in the form of ZnS, in the form of CuFeS2, whatever. But some sulfide ores are present here. Okay. So this dip indicates, right? This dip indicates, number one, the presence of sulfide ores, I can say. Presence of sulfide ores. Second, it basically indicates approximate location, and it also talks about size of ore body. Size of ore body, right? So this is our electrical method or conductivity method, I can say. Okay. Apart from that, there is another method which is also very important, which we call electromagnetic methods. Electromagnetic method. Electromagnetic method. Now, if I'm talking about electromagnetic method, what we do, this is very simple. See, I'll just explain it here. Like instead of passing the current, we send electromagnetic waves. Okay, electromagnetic waves are sent into the ground. Now, if conducting ore is present, if the ore is also conducting, say for example, if like we have taken the examples of sulfide ores, okay, like ZnS, PbS, these are all conducting ores. If the ores are also conducting, they will interact with those electromagnetic waves and it generates a secondary electromagnetic waves. So these ores will generate their secondary electromagnetic waves. Okay, they will generate their secondary electromagnetic waves, which we will detect, and we can basically say that yes, the ore's location, we can find out the location of the waves. Okay, and there are some other methods also, like gravitational method. We'll be discussing it. Gravitational method is there, then seismic method is there. What is seismic method? Gravitational method, though, you will understand, like gravitational method is difference in density of the rocks. By the what we do in the gravitational method, we see the difference in the density of the rocks. Basically, we will look for that what is the difference in the density of the rocks. So that is done by the gravitational method. Okay, seismic method, speed of seismic waves. Seismic means the earthquake waves. So the speed of seismic waves, see this where these ores will be present, there the speeds will be different compared to the other rocks. Okay, so that we can study and we can find out the location of the source. Radioactive methods are also there, detected by Geiger counter. So okay, all these things are there. But now we come to another very important part, which is the sources of metal. Sources of metal. Now, if I am talking about the sources of metal as a whole, basically we have the three sources. One is the Earth's crust. Earth's crust. One source is the Earth's crust. Another source is basically sea water or sea nodules also. And another source is basically scrap. So we'll be talking about these sources now. Okay. So we talk about the first, we'll be talking about the arts crust, right? So if I talk about the arts crust in the sources of metal, if I talk about arts crust, so in the arts crust, you see which metal is most abundant. This is very, very important. As far as PSU exams are concerned, this is very important. They'll simply ask you the most abundant metal in the arts crust, like that. Always remember aluminium is most abundant in the arts class. All other things you remember, you even if you don't remember, but please remember that which is the most abundant metal, followed by what? So aluminium is the most abundant metal, followed by iron in the arts crust. Then calcium is there. Then basically sodium is there. Then potassium is there. Magnesium is there. Titanium is there. Likewise. Okay. So this is the arts class. Okay. So there is tremendous amount of oxygen and silicon is also present in the earth crust. So you can write apart from these metals, a lot of oxygen, and silicon, okay, also present in the earth crust. Also present in earth crust. So this is something which is very important. See, a lot of oxygen is also present. So because oxygen is present, you will always find them in their oxides form. Like I said, aluminium is going to be in their oxides form, Al2O3. Iron is going to be in its oxides form, Fe2O3. Calcium is going to be in its oxides form, but because calcium is more reactive, you see, calcium will not be present in the as CaO. We have seen that calcium is going to again react with silicon, SiO2, silica, and it will form calcium silicate, CaSiO3. Okay, that we already have seen. Now, other important factors. So this is basically one important thing that we need to understand. Okay. Now this is about the arts crust. Now C as a source of metal. If I am talking about C as a source of metal, if I'm talking about C as a source of metal, then seawater, very dilute solution of many elements. Seawater is a dilute solution of many elements. Okay. Around 70 elements have been detected in seawater. You can write it. Around 70 elements, okay, detected in seawater. Right. Now, why? Why so many elements are coming in the seawater? Then we will also see the abundance of the elements. Okay, let us first talk about the abundance. If I'm talking about seawater, the most abundant element is basically seawater I am talking about. So it is not the sea nodules. Always remember, here we are talking about seawater. Chlorine is the most abundant element, followed by sodium, followed by magnesium, followed by sulfur, calcium, potassium, like that. These are the elements, abundance of the elements in seawater. So chlorine is the most abundant element in seawater. Now, if I kind of, if I try to understand one thing, that origin of elements in seawater, how are these elements, means they are coming? Origin of elements in seawater. How are these elements coming in the seawater? That we need to understand. So what are the origin? So one is the weathering of rocks on land. Weathering of rocks. So what happens? The rocks are weathered. Weathered means, see, there is rain. Rain is happening, and the rocks, they are weathered. And when the rocks are weathered by the heat and the rain, the rocks will basically break into smaller and smaller particles. Now, when the rocks, they are basically broken into smaller and smaller particles, these broken pieces will be carried by the river waters. And river water will ultimately make them even more finer. And the rivers are actually going into the sea. And in the sea, these minerals and the rocks are coming. So this is one source. But this is not ultimate. This is one source. Uh, Another very important source is basically what we call juvenile, juvenile, juvenile water. What is juvenile water? If I talk about juvenile water, water released from Earth's mantle, water released, released from Earth's mantle. So see, in the oceans, there are mid-oceanic ridges. Mid-oceanic ridges are there. Means at those points, there are gaps. Okay. At those points, there are gaps. And undersea volcanoes are also there. So through those gaps and undersea volcanoes, okay, these juvenile waters are coming direct. And there are also big cracks in seabeds. So these are the elements that we get in the, what are the elements that we get from the juvenile water? Like chlorine is there, bromine is there, boron, carbon, nitrogen, etc. These all are there. So they are coming from the juvenile. Common salt, they are forming common salt also, like NaCl, MgCl2, CaSO4. And apart from that, there are certain other biological concentrations. Biological concentration. So biological concentration means what? Biological concentration means algae contains very high concentration of iodine. So if there is a good amount of algae, that part will have a lot of iodine because algae contains very high concentration of iodine. Right? And we also have ocean floor nodules. Ocean floor nodules. These are called sea nodules or the ocean floor nodules. So they will have, so nodules means what? They are black lumps scattered on ocean floors. And they are very rich in manganese and polymetallic metals. So they are basically manganese and polymetallic nodules. Okay. This part we have understood. Now we will basically focus on the part which is called the methods of beneficiation. Methods of beneficiation. Right. Now, before extracting metal, we must upgrade the ore. So you just listen, I am telling this part that we need to understand this, that before we go for metal extraction, we need to upgrade the ore. The ore has to be upgraded. Right? Because why the ore has to be upgraded? The ore contains valuable mineral as well as not only the valuable mineral, the ore is also containing a lot of gangue materials. Okay. So ores contains both valuable minerals as well as gangue materials. Right? So because of that, because ore is having valuable minerals as well as gangue materials. Okay. So that is what is uh, because of that, okay, we need to upgrade it because we need the valuable minerals, but we do not need the gangue materials. Gangue materials are not required. Okay. But unfortunately, we are also having gangue materials. So that is why upgradation is important. Now, what is mineral dressing? We use the term mineral dressing. What is mineral dressing? Mineral dressing. So if I talk about mineral dressing as a whole, mineral dressing means removal of gangue. This gangue means what? Gangue means unwanted minerals. Like ore, in the ore, we will have some wanted minerals from where we will extract the metals that we want. And there will be also unwanted particles also. So unwanted particles we call gangue. Okay. So mineral dressing is removal of gangue. You can write removal of gangue. Okay, by mainly physical methods. By mainly physical methods. So we will not employ much of the chemical methods, but see, here also there is a point. There is nothing like that chemical methods we will not be using because we nowadays, even in mineral dressing, the chemical methods, some amount of chemical change in the nature of the mineral is allowed. I will give you an example also. So there is a very big metallurgist, extractive metallurgist, rather I should say, he was Gordon. So Gordon defined the mineral dressing part as the processing of raw materials, processing, processing of raw materials, processing of raw materials to produce marketable products, to produce marketable. I will explain each and every part. To produce marketable products without destroying the physical and chemical identity. Without destroying the physical and chemical identity. Identity. What it means? So we are processing the raw materials. Okay, we'll be processing the raw materials. Why we should be processing the raw materials? To produce marketable products. Okay, we have to ultimately produce marketable products. But we, in the process of processing the raw materials, we should not be changing the physical and chemical identity of the products. Okay. Okay. All of you who are actually there seeing this live, I want all of you to be quite active. Okay. So whatever I ask you, please type. You can actually, if you have any questions also, okay, you can please type it. Okay, that is the main purpose of this class. We want this class to be very, very interactive. So you please do not hesitate. You can type your questions, any doubts you have. Uh, Please let me know. Then I will, because this is, see, you people are actually watching live. So you people will get some extra advantage compared to those who are not here live, watching live. Because see, the same thing they will also get. The recording part is there only, but you can ask questions. So please make use of that. Okay. Now let us see why ore bracing is necessary. Why ore bracing is necessary? Ore bracing is necessary because most ores are low grade ores. So like why ore bracing is basically, if I say why ore bracing is necessary, why is it that the ore bracing is necessary? Okay. So one is that most ores are basically low grades. Most ores are low grades. So from the low grades, if we actually want to extract more metals or the more valuable metals, then ore dressing will become necessary. And rich deposits are also depleting. Means very few places are there which are very, very rich. Rich deposits Rich deposits are depleting. Depleting means are getting lesser and lesser. Okay. So we must upgrade the lean ores. Okay. Now, like I said, that nowadays, okay, some limited chemical changes are allowed. Now I give you an example. So this part I am talking about. Like we defined na, the mineral dressing, it is the removal of gangue by mainly physical method. But nowadays, some limited chemical changes are allowed. Say, for example, FeO, what we sometimes do, we convert it into Fe3O4, which is nothing but magnetite. And then we magnetically separate this Fe3O4. So FeO, we oxidize it into Fe3O4. And then why we oxidize it to Fe3O4? In order to magnetically separate it from the gangue materials. Because if it is in the FeO form, you see, separating it is very difficult. Because we cannot apply the magnetic separation in the Fe. But Fe3O4, which is magnetite, is strongly, it is basically paramagnetic. Now, that means it is what? It is basically, it is strongly attracted by magnets. So, we can separate it by magnetic methods. Okay. Now, you see, so ore dressing, I can say that as a whole, I can say that ore dressing involves, what are ore dressing involves? It involves the physical treatment, number one. It involves limited chemical change or composition. Okay. Now, unit operations in mineral dressing. Very important concept we are starting now. Unit operations in mineral dressing. Unit operations in mineral dressing. So what are the unit operations in mineral dressing? We will see. One operation is what we call comminution. Comminution. So what are comminution? Comminution means, it means breaking a particular material into smaller and smaller pieces. So suppose this was my material. I will break it into smaller pieces like this. Again, this I will break it eventually into more smaller pieces. Okay, like this. And I will eventually break it into even finer pieces. Okay, so this is basically comminution. So comminution involves crushing and grinding. Crushing and grinding. Both are nothing but breaking large lumps into smaller pieces. Breaking. So this is the first step. Breaking large lumps. Because in the ores are always as rocks, big lumps. So you are breaking large lumps. We need to break them, okay, into smaller pieces, right? So what is the thing that we are exploiting here? We are exploiting brittleness of the material here, right? Now, after the crushing and grinding is over, then we will go to the next part, which is called sizing. Sizing. Sizing means what? Sizing means we are going to size the materials. Size the materials means we are going to screen them. This sizing have two parts. One is called screening, another is called sorting. Here, screening or sorting means we are going to separate the materials based on their size. Separate the materials based on their size difference. Then after that, we will go to hydraulic classifier. Hydraulic classifier. Okay. So what this hydraulic classifier does, this is basically nothing but it uses the settling method. Means, see, these particles that we have actually crushed, these particles will be of different sizes. Okay, there is going to be size difference. Plus, different particles will have different density also. Ore will have some density. The gangue material will have some different density. So that if I kind of what happens is if I suspend them in a liquid, suppose this is a liquid. Now, if I put all of them in a particular liquid, the settling speed means the speed with which they are actually coming down. That is not going to be the same. You can very well understand that if the ore is heavier, it is going to settle faster compared to the gangue material. If it is lighter, it will take more time to settle down. So exactly that we use in settling in the hydraulic classifier. So we'll discuss about hydraulic classifier in detail, but the mechanism that is used is settling in fluid. While I am writing this, there is a particular reason behind it. What is the reason? In the examination, sometimes they directly ask questions. They'll not definitely ask you that definition, but what they can ask you is that they'll say hydraulic classifier. So, and they'll say that hydraulic classifier, what is the property that it uses? Settling in fluid, या फिर surface tension, what property they uses? So definitely hydraulic classifier, if you know that it uses the settling in fluid, then you can directly answer the question. Okay. So apart from a hydraulic classifier, there are other methods also after hydraulic classifier, which we call concentration methods. Now, concentration methods, as far as concentration methods are concerned, they are very, very important and they are the heart of mineral beneficiation techniques. There are different kinds of concentration method. We'll be talking about them. There is a heavy media separation. We talk about heavy media separation. Then we talk about jigging. We talk about tabling. So these are various concentration methods that we will be talking about. Okay. Now, this heavy media separation we have talked we have talked about the heavy media separation, then jigging, tabling, whatever. So these all actually exploit or use the difference in density. So they use the density difference method. So because there is difference in density between the different parts, that is exactly what they are being using. Difference in density of the materials. Okay. So this part, I think you have understood. Now, apart from that, we have talked about the magnetic separation. We have talked about electrostatic separation. Yes, there is another method, what we call the flotation. Now, flotation is what basically, if you talk about flotation method, this is froth flotation. Now, you see what happens in case of flotation. Suppose I have a mineral. Now, that mineral, some of the minerals, what happens is the minerals can be two types. One is that can be, if I have a mineral, it can be hydrophobic or it can be hydrophilic. What does hydrophobic means? Hydrophobic means that phobic means afraid. So I always remember phobic means afraid. Hydrophobic means afraid of water. So the mineral surface is afraid of water means what? How can a mineral be afraid of water? Obviously, the mineral is not afraid of water, but what it basically means is that the mineral surface is not weighted by water. So water will not stick to the mineral surface. Water will not stick to the mineral surface. That is, the mineral surface is hydrophobic. Now, if a mineral surface is hydrophobic, then what happens? the air particles. If water is not going to stick to the mineral surface, then what is going to stick to the mineral surface? If I have a mineral like this, instead of water, air bubbles will stick to the mineral surface. And these air bubbles will make this mineral, light, obviously, because they are air bubbles. And they will take these minerals up in the froth section. We will see what is this froth section I'm talking about. So this phenomena we use in the flotation when I'm talking about the flotation, right? Now, flotation mainly sulfide ores are used. So sulfide ores are used in through this process. Like copper sulfide, you can have the lead sulfide, we can have the zinc sulfide. This is the beneficiation method we use is flotation. So after the flotation, apart from flotation, we can also have agglomeration. Agglomeration. So in the agglomeration, what are the steps of agglomeration? Pelletizing, nodulizing, 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 and sintering. Right? So purpose is to make small particles into large lumps. Into large lumps. Okay. So I want to ask one thing. Do you know any of you that agglomeration? Just give me an example where we use this agglomeration, or where you have seen that the agglomeration to happen. So it can be pelletizing, sintering, nodulizing. In means in the comment section, you can please comment. Have you seen this? Means have you studied anywhere? Please comment in the comment section if you have seen. So see, this we actually use in solid-solid reaction, where solid-solid reaction is very, very important. We will like agglomeration, like pelletizing or nodulizing. So where we use it? Iron ore sintering. Before blast furnace, before charging them in the blast furnace, the sintering is basically done. So iron ore is basically sintered, agglomerated, and then it is charged in the blast furnace. Always remember that. Right? Okay. Now, now we will talk in detail. Each and everything that we have studied. Now we will talk in greater detail. So comminution, if I am talking about comminution, right? Comminution is nothing but it is size reduction. Comminution is size reduction. Right? So the two main purpose of comminution is, what are the two main purpose of comminution? Two main purpose. The two main purpose of comminution, we can say that one is liberation of valuable minerals. Liberation of valuable minerals. And second part is basically production of small particles suitable for further beneficiation. What I mean by this? We'll see. Suitable for further beneficiation. So see, what happens if I simply tell you that what happens here? See, suppose try and understand this very important. This diagram is there in your HSRA book. So let us understand what it means. So none of you are actually writing anything in that type message. So okay. Anyways, we'll understand what this means. Just a minute. Let's draw the diagram. Suppose these are what? These are nothing but minerals. Okay. This is mineral of type A, suppose, and this is type B minerals. These are type B minerals, suppose. And these are the particles, like particles of B, particles of B, but this is particle of A, this is particle of A, something like this. Okay. Now they are basically packed like this. Now, in the comminution technique, when we are actually crushing or grinding them, what happens? We are breaking them. In the process of crushing and grinding, we are breaking these particles into smaller and smaller pieces. Now, when these particles will break into smaller and smaller pieces, they can break in different ways. Like, what are the ways in which they can break? They can break, the particles can break like this. The crack can happen. One, the crack can happen like this. Another, the crack can happen through the border also. Border means boundary. So in between B and A, they can break. So the B is going to be separate and the A is going to be separate. If it is along the border or the boundary, then it is breaking like this. But if it is not along the boundary, then what happens? Interparticle breaking, intraparticle breaking. So then the particle will break and be smaller size. But anyway, one thing you understand that by the process of comminution, what is actually happening? By the process of comminution, actually liberation is taking place. Liberation means what? The particle B and particle A, they were basically particle particle B and particle A, they were basically fixed together. Okay. But the process of comminution, through this process of comminution, what happened? Through this process of comminution, okay, we have liberated the particles. We have liberated the particles. So this is exactly what we try to achieve by the process of comminution. So the fractures, like I said, the fractures through grains, it can take place. The fractures that can take place, fracture along grain boundaries, it can happen. Like one is the fracture along grain boundaries. Fracture along grain boundaries, and the other is basically fracture through grains. Fracture through grains. Like now, if bonding is basically very strong, then the fracture through grains will happen. Now, if bonding is not that strong, the fracture through grain boundaries will, right? Now, one thing is basically important to understand that if fracture through grain boundaries is happening, then liberation is taking place. Because see, grain boundaries के मतलब अगर grain boundaries से fracture हो रहा है, तो क्या हो रहा है? Instantly it is getting liberated. Okay, B is getting separated from A. But if it is not happening like that, if fracture through grain boundaries is not taking place, then what will happen? Then we need more comminution, means more crushing is required in order to separate A and B, right? Now, let us see what is crushing. Crushing means there is a very, very important concept, crushing and grinding. The difference you will understand. Crushing means reducing the size of a material to 6 millimeter. So down to about how much? Average size is 6 millimeter, not less than 6 millimeter. So if you are grinding, see, if you are reducing the size by hammering something, and the average size is basically 6 millimeter, or the lower limit is 6 millimeter, means you are not reducing the size less than 6 millimeter. Maximum you are reducing up to 6 millimeter. Then you will call it crushing. So acts mainly on major factors. Crushing, it acts mainly on major fragments. Acts mainly on major fragments. And crushing is basically, I can say, crushing is less selective. Less selective. Right? So what are the machines that are there for crushing? Machines. Machines are number one, jaw crushers. Jaw crushers are there. Okay. Apart from jaw crushers, so these knowing the names of the machines are also very important. Gyratory crushers and roll crushers. So these are the machines. So ore is crushed before. So in each and every machine, there is a hard surface, something like this. And the ores are basically crushed with this hard surface. And there is a movable surface also. So suppose this surface is movable and this is fixed. And you are taking the ores in between and then you are crushing it. Okay. So this is the mechanism which basically the crushing is basically taking place. Right. Okay. Now, grinding. Now, let us talk about grinding. Now, when I talk about grinding, it is below 6 millimeter. Grinding is below 6 millimeter. So that means you are reducing the size to below 6 millimeter. Finer reduction, and it is more selective also. What are the machines? What are the machines involved? We have ball mills. We have ball mills. We have rod mills. And we have what else? Tube mills. Right? So grinding, we are actually making it more finer. So grinding is slower than crushing, I can say, because we are making the particles more fine. Is the next step. After crushing comes grinding. So grinding is slower than crushing. Okay. Now let us understand. Let us understand one thing. Ball means working. How ball means work. So all these things, if you understand the working of the ball mills, then you will understand the rest all. Because ball mills, pebble mills, they are all the same. Rod mills. So in the ball mills, what happens is there is a vial. Vial means nothing but there is a something like this. This we call a vial. 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 Inside these vials, there are many balls, hard balls. These are basically very hard surface balls. Generally made up of tungsten. Okay, tungsten carbide. Very hard surface balls like this. Now, many balls are there, and you will take the ores, the ore particles that need to be crushed. So suppose these are your ore particles. So you have taken the ore particles. Okay. You have taken the ore particles in the ball mill. And you will close the lid of the ball mill. There is a lid also. You will close the lid of the ball mill. And what you will do, you will rotate this ball mill. This ball mill is actually rotated. Now you see, when this ball mill is rotated, these balls, hard balls, will actually hammer this. They'll have some centrifugal force or whatever because of the rotation. Kinetic energy is going to be there. And these hard balls will hammer or impact these ores or the ore particles. They will impact the ore particles like anything. Now, when they impact the ore particles, these ore particles will break into even smaller and smaller pieces. These ore particles will break into even smaller and smaller pieces. Okay, this is basically the working of the ball mill. Now, when we talk about the working of the ball mill, there are certain things we need to talk about. What are the interactions that are basically taking place inside that we will now focus on? There is cataracting. What is cataracting? Cataracting means nothing but impact with balls, rods, and pebbles. Direct impact. So direct impact with the ores, right? So the balls are actually hitting the ores directly. That we call cataracting. So cataracting means impact with direct impact with balls, rods, and pebbles. Right. So this is nothing but cataracting. Then after cataracting comes cascading. Now what is cascading? Cascading means it is attrition between the rolling balls. Attrition between rolling balls. Okay. Attrition between rolling balls means that these balls will basically, there is going to be the force of attrition means there is going to be like friction between the balls and the friction. Due to the friction, these ore particles will even break into smaller particles. Okay, that is cascading. Third is basically interparticle collision. Even the particles will collide among themselves also. So there is going to be interparticle collision and rubbing. And fourth is going to be friction with lining. So friction is also there. Sir, कुछ order करिए ना आने. You had your name. Friction with lining. Okay. So we'll see. See, there is something we need to understand. Effect of speed. What is this effect of speed? See, what we discussed just now. This is the ball mill, right? Now, if suppose the speed is too high, then what is going to happen? We'll see now. If the speed is too high, what will happen? If the speed is too less, what will happen? And things like that. Okay. So if the speed is too high, then what is going to happen? If the speed is too high, then the centrifuging occurs. What is centrifuging? Centrifuging means क्या है centrifuging? Suppose this is a vial and we are rotating the vial with a very high speed. The balls will stick to the walls of the vial. They will not impact the ores. They will not fall on the particles. They will not impact the ores. So the balls will stick to the walls of the vial, something like this. because of the high centrifugal force. Okay. So the centrifugal force, you see that if it is rotating, there is going to be a greater centrifugal force this side. So that force is going to make the balls stick to the walls of the vial. Okay. So this is called the centrifuging. So what happens? Balls stick to the walls. Balls stick to the walls. Balls stick to the walls. So no grinding. No grinding takes place. Okay. And if speed is too low, if speed is too low, then what happens? If speed is too low, then only cascading. Cascading means, see, cataracting is not happening if the speed is too low. That means impact, direct impact between the balls and the ore particles not happening. Then what is happening? The attrition between the rolling balls. This is happening. Okay. So if speed is too low, only cascading. Cascading means attrition between rolling balls. This step is happening. Okay. So you can say this will give rise to limited grinding. So grinding is going to be less. Limited grinding. Okay. Now we have three golden laws that we will basically understand now. These are called the three golden laws of comminution. Very important. Laws of comminution. You can write it. How you expect questions from this? Like in the MCQ, they can ask that, they can give you 3 laws or 4 laws in the option. One of them are going to be the laws we are discussing now. And the question would be something like this, that which of these following laws are related to the comminution technique? या फिर comminution. So directly, if you know, you can answer. Okay. So the one of the law is what? First law that we will study is what we call Rittinger's law. Rittinger's law. Now, what this law tells us, what Rittinger's law talks about. Rittinger's law says that the energy required means the energy required for breaking a material into smaller and smaller particles. So the energy required is directly proportional to the new surface area created. New surface area created. What is meant by this? Try to understand what this is telling. The Rittinger's law is telling that energy required is proportional to the new surface area created. That means when particles are broken into smaller pieces, new surface is generated. And more particles we are breaking into smaller and smaller pieces. What is happening? If we are breaking more and more particles into smaller and smaller pieces, then what is happening? The surface area is even becoming more and more. So ultimately, the finer you are going, the finer particles you are making, more energy you will require. Say, for example, if suppose this is a big lump of a particle. Now, this lump I am breaking into 2 pieces. Obviously, I need some amount of energy to break this lump into 2 pieces. But see, if I try to break this lump into 2 pieces and this lump into 2 pieces, I will require more energy. Because the more finer particles I am making, the surface area is increasing, and more new surface area is increasing, the energy required is directly proportional to it. So it means that more finer the particles you make, the more energy you require. Okay. So that is what is basically our Rittinger's law. Okay. That is our Rittinger's. Now, there is another law, second law, what we call the Hicks law. What Higgs law is talking about? Higgs law is also something similar to Rittinger's law, but there is a fundamental difference between that. We need to understand that fundamental difference. I'll explain that to you. So in Higgs law, it talks about energy required. Higgs law says that energy required is directly proportional to the size reduction ratio. Size reduction ratio. That means E is proportional to ln d1 by d2. That means what? Higgs assumed that, Higgs said that, you see, the energy depends on the percentage of size reduction. It does not depend upon the actual size. How much size reduction is taking place? How much size reduction is taking place? Only that is important. Okay, not the actual size. So energy is not dependent upon the actual size. Like in Rittinger's law, we saw that what Rittinger's law said, that energy is dependent on the actual size. But Higgs law is saying that no, that is not the case. It is the size reduction ratio. Okay. And third is our Bond's law. And what Bond's law says? Bond's law says that the work input or the energy, work input is inversely proportional to square of the product size. To square of the product size. What it means is that I can say, if I talk about Bond's law, E is proportional to 1 by root over d2 minus 1 by root over d1, where d1 and d2 are nothing but the particle size. d1 and d2 are particle size or particle diameter. Okay. But there are certain limitations also of these, sizes and all. Now, what are the limitations? The main limitations are basically, if I talk about the limitations are the surface measurement is arbitrary, like the size we are talking about. I am talking about the size. So how you will measure? When the particles are becoming very finer and finer, it is very difficult to measure the size like that. The cracks inside particles not counted. So these are some of the limitations. So, okay, now these are some of the limitations we have talked about. Now, I tell you one of the method of finding the particle size. Let us see. One of the method of finding the particle size. It is sieving. Now, sieve, everyone, all of us have seen actually in our kitchen. Sieve is nothing but that part which is like this, ऐसे oval shape का होता है. A net is there. So you have seen in the kitchen, your mother, using this sieve in order to, she uses this kind of sieves in the kitchen for the flowers. So flowers will be, poured in this part, and then this sieve is going to be jerked, and then finer particles will come out, and coarser particles will get retained here in the nets. So this is basically nothing but the main mechanism of sieve. So sieve means basically there is a mesh. So this mesh has some mesh number also. Now what is mesh number? Mesh number means, this is very important concept. Mesh number means the number of, so if you magnify this and if you see, you will see that this mesh is nothing, this mesh and nothing, but they are something like this. Like this. So square, there are many square openings. These are all square openings. You see, this is a square opening, this is a square opening, this is a square opening, this is a square opening. Now, if I try to calculate that how many square openings are there in 1 inch, 1 inch, 1 inch in a line means linear inch. So along this line, suppose I want to find out along this line ki how many square openings are there. So mesh number is only talking about that. Mesh number is number of square openings, number of square openings, number of square openings per linear inch, per linear inch. And 1 linear inch is how much? Basically 25.4 millimeter. 1 linear inch is 25.4 millimeter, right? So if I say that mesh number is 200, what it means? 200 mesh number. 200 mesh number means basically 200 openings per inch. 200 square openings. Square openings per inch. And if I say 300 mesh number, then what will it mean? 300 mesh number means, it means 300 square openings per inch, right? So 200 mesh number is 200 square openings per inch, then 300 mesh number will be 300 square openings per inch. Now if I ask you that, okay, now tell me which is finer. Now in 1 inch, 200 opening, that is going to be finer, or in 1 inch, 300 opening is going to be finer. You will say that obviously in 1 inch, 300 opening is going to be more finer because the openings are smaller in size. So that means that if the mesh number increases, your openings are becoming smaller and smaller. So if you are going for higher mesh number, your openings are actually becoming smaller and smaller, right? So that is the main idea. You should always remember this. Now there is a particular series we call Taylor series. Now what is Taylor series? Let us understand this Taylor series. Okay. Taylor series होता क्या है? Now it follows GP. Taylor series, it follows GP, means geometric progression. Okay. Now the ratio is basically root 2 or 1.414, whatever you say. Now that means, suppose I am giving you an example what it means. If 200 mesh number, you see the size is fixed. 200 mesh number means 74 micrometer. What I mean by this means, if a mesh is, say, if there is a mesh of mesh number 200, if there is a mesh of mesh number 200, it means that 200 means that uh, each square inch is going to be of 74 micrometer. Or you can also say in this way that the particle which will pass through this mesh is going to be of the average size of 74 micrometer. Okay. Now, now if I ask you that just one mesh number ahead or below, so ahead means you will say that it is nothing but 74 root 2. So you will multiply it with root 2. And that is basically next above. It is going to give you 104 micrometer. Okay, something like that. And below, you will say that it is basically nothing but 74 by root, which is 52 micrometer. Now, if I ask you that 174 micrometer, sorry, 104 micrometer. Now this is 74 micrometer, mesh number is 200. So 104 micrometer, the mesh number will be more or less. Obviously, the mesh number should be, see that it is what? It should be more or less. So if the mesh number is more, it will becoming more and more finer, right? So you can now understand yourself that what should be the mass number, right? Now, we'll talk about classification and concentration. Classification and concentration. Now, if I talk about classification and concentration as a whole, then let us understand. Classification depends on the, what is classification? Classification depends on the settling rates of individual particles. So I can say classification, it depends on settling rates of individual particles in the fluid medium. Okay. So how easily they are basically settling, the individual particles are settling. That is basically classification. So controlling factor in classification is different settling rates between particles of different sizes and different specific gravity. What it means is that you see these settling rates, the settling rates of particles, they are basically dependent upon, one is size and another is the specific gravity. Specific gravity means density. So more dense particle, they are going to settle faster. Okay. And less dense particle, they will settle at a slower rate. Let us. So specific gravity, if I'm talking about specific gravity, a particle of higher specific gravity settles faster. A particle of higher specific gravity settles faster. Right? Then if I talk about the shape of the particle, then you can say a rounded particle settles faster. A round particle settles faster. Now, if I talk about the size, you can very easily say that a larger particle settles faster. Right? If I talk about air bubbles, you will say that a particle that does not attach or retain air bubbles settle faster. Because we'll see that do not retain air bubbles settle faster. Because if a particle is getting attached with air bubbles, what will happen? The particle will become lighter. So it will settle slower at a slow rate. Fifth, magnetism. So what happens? Particles that have mutual magnetic attraction, what should happen? They should settle faster. Why? I tell you. Particles that have mutual magnetic attraction, mutual magnetic attraction settle faster. Okay. Now, why is it? Because you see, suppose this is a particle, this is another particle. Now, if these particles are having mutual magnetic attraction, they will cling together. They'll just attach together and form a one particle, something like this. So this has become a comparatively larger particle, na? So its weight will also increase, everything will increase, it will settle faster. So they become coagulation of many particles. Okay. Then sixth, density of the liquid. Density of the liquid is also important. Why? Because settling rate higher in lighter liquid than in heavier liquid. Settling rate. If all the other factors are same, settling rate is higher in lighter liquid compared to heavier liquid. Okay. And viscosity. The last point is viscosity. So when I'm talking about viscosity, settling rate obviously higher in less viscous liquid. Settling rate of particles is higher in less viscous liquids. Okay. Now, settling, now you know what are these settling rates and we have discussed. Okay. This part we have discussed. Now we will talk about a particular method which is dependent on this settling rate, which is called heavy media separation. Heavy media separation, HMS, right? Heavy media separation. What is this heavy media separation? It is basically a gravity separation process which is based only on specific gravity difference. This is a gravity separation process based mainly on specific gravity difference. Based mainly on specific gravity difference. Now, particle size does not matter here. Particle size does not control the separation. Only density controls the separation in case of heavy media separation. So let us understand the working principle. Let us understand the working principle in case of our heavy media separation. So what is the working principle? First, okay, I'm not writing it. Just understand. First, what happens? The ore is crushed. Okay. And it is placed in a liquid whose density lies between the density of the valuable mineral and the gangue. So the density of the liquid, it should lie between the density of the gangue and the density of the mineral. So exactly this is heavy media separation. What happens? You see, liquid means the medium. If I have taken a medium, something like this, okay. Now this is the media we have taken. This is the medium we have taken. This is the medium. Okay, so let us see. This is what basically, this is the medium, right? So if the density of the medium is like is in between, so the minerals, if the density of the mineral is more, then what is going to happen? The minerals will come and settle at the bottom, right? Because the density of the mineral is more, so they'll come and settle at the bottom. But you see, the density of the gangue is less compared to the density of the liquid. So the gangue will actually float here above. So these are the gangues. So gangue means unwanted particles. They'll float. So you can very easily separate the unwanted particles from the minerals. Okay, the minerals that we actually want by the heavy media separation. Okay, so you can say the valuables here. What happens is the valuable, they basically, what happens? It sinks. Valuable sinks. The valuable sinks, and the gangue floats. Right? So this is exactly what happens. So if I try to give you the example, right? Say for example, like metallic oxides. If I take the example of metallic oxide. So metallic oxides, if I am taking the example of metallic oxide. So metallic oxides, it is basically uh, 3.5 to most of the metallic oxides will lie in this range only, 3.5 to 4.5 gram per centimeter cube. This is the density. And if I talk about the density of the most common gangue, which is silica, which is a gangue. So the density is going to be 2.65 gram per centimeter cube per cc. And if we make the density of the medium, if we can make the density of the medium to be 3 gram per cc, then you see the metallic oxides will have more density compared to the density of the medium. Okay. And the silica will have less density compared to the density of the medium. So ultimately, what will happen? The metallic oxides, metallic oxides will basically sink. Okay, metallic oxides will sink, and the silica will float. Silica will float. So this is exactly what happens. So now there are also ways to prepare the suspension of fine heavy particles in water. Okay, so common heavy media uh, materials that we use, you can write it, common heavy media materials, means common materials that we actually use to make this uh, what to say, to make this medium for the heavy media separation. So what are they? They are, one is galena, PBS, very important, and another is ferrosilicon. We also use ferrosilicon. So these are the most common materials that we basically use. Right. Now, this was all about the heavy media separation. Right. Now, we have also seen about the magnetic separation. Like ferromagnetic, they are strongly attracted. Paramagnetic, they are weakly attracted. Electrostatic separation also we have seen. Now we will talk about a very important separation method, which is called the flotation. Flotation, and this is sometimes also famously called froth flotation. Flotation or froth flotation. So what happens here? We need to understand. So there is a pulp. In this froth flotation method, there is a pulp. Okay. There is a pulp, and this pulp is basically having ores also. Ores are mixed in this pulp. Now, air is basically blown. Air. Air is blown in the pulp. So because air is blown in the pulp entirely, so this pulp is basically going to get what? This pulp will get agitated. Agitated. Pulp will get agitated. And when this pulp gets agitated, what happens? There are froth. Froth means, I tell you, froth means what? There are froths like this. Okay, that are going to be just on the top of this overall, on the top of this pulp. There will be froth, right? There will be froth on the top of this pulp. And in this froth, we will find our valuable minerals. Okay. And what is going to be left behind at the lower part of this pulp is going to be our gangue materials. So let us understand why this happens. Basic principle. Very important, this method, froth flotation. So the basic principle, first is pulp agitation. So we will agitate the pulp. So we call it pulp agitation. Second is basically air is blown. Okay. And froth is produced. Froth is produced. Now some minerals, mostly sulfides, what happens? If I'm talking about some minerals, let us see now. Mostly sulfides, if I'm talking about. Now you see what happens. When I am blowing the air, inside this pulp, when I am blowing the air, okay, and the pulp is getting agitated, okay, these sulfide ores, suppose these are the sulfides, these sulfides will attach the air bubbles. These are suppose my air bubbles. This is the sulfide ore or the sulfide. This sulfide is attaching suppose this is the zinc sulfide, ZNS. It will attach the air bubbles in its surface, or the air bubbles will get attached to this zinc sulfide like this. Okay, in its surface. Now, as the air bubbles are getting attached, you can understand that the air bubbles will always have a tendency to move up. So this sulfide is going to move up from this inside the pulp. It will eventually move up and come to this froth section. Okay. And from this froth section, you can very easily skim this froth section. Skim means separate this froth section and get the sulfide ores. Okay. So you can write that some minerals, mostly sulfides, attach air bubbles, and they, after attaching with the air bubbles, they rise with water. Rise with froth. Okay. And what happens to the gangue? The gangue sinks. Because gangue is not attaching with the air bubbles. Okay. Now, we need to understand what is the surface property that is exploited in the froth flotation method. Okay. What is the property that is exploited? Property exploited in froth flotation. What is the property which is exploited in froth flotation? The property which is exploited is basically surface property. Surface property like wettability. Direct one-liner question comes. Direct one-liner question comes from you. So surface property like wettability is exploited. So you see, like we discussed earlier also, hydrophobic part, the mineral which is hydrophobic. Hydrophobic means afraid of water. It is going to get attached to air bubbles. That mineral which is hydrophobic will get attached to the air bubbles. And hydrophilic mineral or hydrophilic portion, it will remain in water. It will remain in water, you can say. Now, when we talk about this froth flotation, okay, there are certain things we need to talk about them also. Like flotation reagents, you can call them reagents, very important. And we will see their functions. Okay, from their functions, direct questions come. Flotation reagents. What are these flotation reagents? One is the pulp. Okay. Now, when I talk about the pulp, this is suspension of fine ore particles in water. Pulp is nothing but suspension of fine ore particles in water. Right? This is pulp. Second is basically frother. Frother is also there. Now, what are frothers? Frothers, they produce small stable bubbles. Produces small stable bubbles. Means air bubbles. And it stabilizes froth. So, see, only froth is not enough. Froth has to be stable also. It has to be stable also, so that the froth is not going with time. So it has to be stable. Exactly that is what is done by the frother. One of the very important example of frother is basically pine oil. Please remember this example. Many a times in GATE, they have asked, the pine oil is what? It is frother or activator or collector or things like that. Okay. Now, these are the two, pulp and frother, we have discussed. Now we will talk about collectors. We'll talk about collectors. Now, what are collectors? Collectors means, you see, collectors are certain substances which modifies the surface properties by adsorption or chemisorption. We will understand what it means. Modifies the surface properties of the minerals. Modifies the surface properties of the minerals by adsorption, or we call it chemisorption. What I mean by this? That means what happens is, you see, if I have a ore or a sulfide, now I want to actually remove this sulfide by the froth flotation method. Okay. by the froth flotation method. I want to have this removed sulfide. Now, if I'm putting collector, what will this collector do? This collector will first and foremost, they'll get themselves stick to the surface of this sulfide ores or this sulfide. They'll stick. This is called adsorption. Adsorption. They'll stick to the surface like this. They'll make this surface more effective so that air bubbles can stick to this surface. That means collector will make this surface more hydrophilic. Sorry, more hydrophobic. Because if a surface is more hydrophobic, that means if it is afraid of water, then the air bubbles will stick more. So the collector will exactly do this. It will make the surface of the minerals more hydrophobic so that the air bubbles now stick to the surface of the minerals and the mineral directly goes to the froth. So collectors stick to the mineral surface. You can write collector stick to the mineral surface. Collectors stick to the mineral surface and makes it hydrophobic. Hydrophobic. So air bubbles, it allows the air bubbles to attach to the surface. To attach to the surface, right? One of the very important example of collector is xanthates. Examples, please remember. Right? Now, collector to ho gaya. Now we talk about activator. Now we talk about activator. Now, what are activators? It makes minerals more receptible to collectors. Active see, collectors are making the mineral surface uh, hydrophobic so that the air bubbles can directly attach to them. So I can say that collectors are making the mineral surface more receptible to the air bubbles. And what are activators doing? Activators are improving the role of the collectors. They are like, you can say they are encouraging the collectors. So activators, they makes minerals more receptible to collectors. More receptible or receptive, more receptive to collectors. So collectors can work more well. So collectors wants to stick, activator prepares the surface, basically. Some of the examples of activators is copper sulfate. So copper sulfate activates the ZNS, zinc sulfate surface. And like we have the activators, in the similar manner, we also have another thing, which is called the depressor. So what are depressors? You see, it prevents collector from attaching. So depressor just does the opposite role. It prevents the collector from attaching. From attaching to the mineral surface. To the mineral surface. So this is exactly what is done by a depressor. It keeps the mineral hydrophilic. It keeps the mineral hydrophilic. Right. So these are mainly, this was our froth flotation. as a whole we have discussed, right? One last thing I would like to discuss about the, see, we have discussed the Froth flotation everything. Now weightability. The Froth flotation is basically dependent upon the weightability only, that we understood. Because why weightability? I said that, see, this Froth flotation method is basically doing what? That which mineral is hydrophobic, which mineral is hydrophilic, on that it is dependent. So just understand this. Suppose this is a liquid. This part that we have drawn, it is a liquid, this portion. Okay. This entire portion is liquid. Okay. On the solid surface, this surface is solid. So there is basically a liquid drop on the solid. This is a solid surface. Okay. Now I can basically, now I can draw the surface tensions. So this is basically the gas. This part is the gas. This is the liquid. This is the solid. So this is the surface tension between the liquid and the gas. Liquid and gas surface is there. This is the, this part is the, this is basically gamma between liquid and solid, liquid solid. And this part is basically our gamma between solid and gas. Right. If this is angle theta, suppose it is making an angle of theta, this much is the angle theta. Then what I can say? I can say gamma solid gas, gamma solid gas. Solid gas means this. Gamma solid gas is equal to gamma liquid solid plus gamma liquid gas cos theta. I can say this very easily. Because this liquid gas cos theta, if you break, it will have one component along the gamma liquid solid. So from here, you can say that cos theta is nothing but gamma solid gas minus gamma solid liquid divided by gamma liquid gas. So this equation you will get. Now your theta is basically dependent upon, or your cos theta value will depend upon the surface energy between the solid gas, the surface energy between the solid liquid, and the surface energy between the liquid gas. Okay. Now if the theta value is basically 0, when the theta value is 0, the cos 0 is basically how much? Cos 0 is 1. We say that it is completely weightable, complete weighting. Complete weighting. When theta value is 0, it is complete weighting. Okay. When theta value is basically less than 90 degree, that means partial weight. Partial weighting. And weak flotation tendency. Partial weighting will be there. Partial weighting and weak flotation tendency. Weak flotation tendency. And when the surface will have a theta value greater than 90 degree, then what happens is it is non-weighting. Non-weighting, the surface becomes hydrophobic and strong flotation tendency. Strong flotation tendency. Right? So, with this, we have come to the end of our mineral beneficiation technique. Thank you for joining this class. I think this class was useful to you. We have completed in detail all the methods of mineral beneficiation. I think it is going to be very helpful for your upcoming examination and your SAIL exam as well. For more such classes, please stay connected with MetaGate and subscribe to our channel. Thank you.